Okay, so let's start our lecture today. So the first thing I'll finish is that the last part of the chapter on Hamiltonian mechanics, which is the canonical transformation, right? So I started this part of the chapter last time, and today I'll finish it. And last time I already mentioned that the canonical transformation part, okay, so of this chapter won't be in your exam. Okay, so let me say it one more time, okay? So then you might kind of relax a bit. So it's after the midterm, right? So I will just finish it anyway, and then after that, I'll go to the next part of the. I'm sorry, the next chapter. Okay, so that chapter will be on in the final exam. Okay, so but that's the next chapter. So what did we do in the last lesson? Okay, so I was telling you that so there's a transformation that we are trying to achieve, which is known as the canonical transformation, right? So first of all, right, so I told you that in the Lagrangian formulation, right, so if we are going to do the so-called the coordinate transformation, or known as the point transformation, right, so after you do that, you don't really worry about that whether the form of the Lagrange equation will change, right? The form of the Lagrange equation will still be the same, right? So but of course, as I remind you multiple times already, the form of the Lagrangian itself might change. Okay. So, however, when we do the transformation, okay, in the Hamiltonian formulation, okay, so the transformation that we did, okay, so it's no longer the transformation for the spatial coordinate only, right? So we were doing the transformation that will transform both the spatial coordinate and also this momentum coordinate, right? So that's the kind of the transformation that we're trying to do in the Hamiltonian formulation, right? So because remember, when we use the Hamiltonian formulation, right, so we think of the so-called the phase space, right? So both the spatial coordinate and the momentum coordinates, they are coordinates in the phase space. Okay. So in this sense, they are treated equally. And last time I showed you this example, right? So with this simple harmonic oscillator, okay, so is that if I go to start with this Hamiltonian, and then if I just make this, well, I still call it coordinate transformation, but you remember that this also not just change the spatial coordinate, but also the momentum coordinate, right? So and I made this transformation, and then I make the Hamiltonian becomes this form, right? So but then if I try to if I assume that the form of the Hamiltonians Hamilton's equations are still the same, right? So which are these two, and then I will just get some result that obviously wrong, okay? And that means, right, when you do such a transformation, right, so there's never guarantee that the form of the Hamilton's equations are preserved, okay? So then, as I said, so we are looking for this kind of special kind of transformations, is that after we do such a transformations, okay, so the Hamilton's equations, okay, so still take the same form, and this kind of transformation is known as the canonical transformation, okay, right? So originally we start with this set of coordinates Q, I, and Pi, right? So these are the Hamilton's equation. After the canonical transformation, okay, so the Hamiltonian will be expressed in terms of this capital Q and capital P, and I call this new coordinate new Hamiltonian as capital K. And then the Hamilton's equations, okay, so are still taking the same form. Okay, so you can see that just that this small q becomes this big Q, this small p becomes this big P, right? And this H becomes K. Okay. Right. So then this question, right? So how do we find the relations, right? So between the old coordinates and new coordinates, which satisfies the requirement of canonical transformation. Okay. So remind you of the basic facts, right? So remember that how did we get the Hamilton's equation of motion from the first place, right? So we started with this so-called modified Hamilton's principle, right? So still remember that, and we do calculus on variation, right? So on this, and then we obtain the Hamilton's equations. So right, so now that if we want the form of the Hamilton's equations to be preserved, so that means that, so now let's say I have done the transformation already, right? So then this will be my new coordinate, right? P and Q, and then this is a new Hamiltonian. Then that means that if I put this new integrand, right? So into this integral, and then again do the calculus of variation, right? So, and if I if this is still satisfied, right? So then I will get the same form of the Hamilton's equation, right? So, however, right? So just comparing this equation here and this equation here does not really give any insight on how to make the transformation, right? Because I'm just this form is just exactly the same as this form, right? So then the trick is that we're going to add an additional term to this integrand. Okay. Right. So suppose I've already know that this is satisfied. Okay. So now I'm going to consider this integrand to be modified by adding this additional term. Okay. df dt. Okay. So remember, okay, so this is not partial f partial t. Okay. So this is df dt. And f itself, right, so it can contain time explicitly, but also it can it might also not contain time explicitly, right? So and so this is an arbitrary function. Okay, so this is an arbitrary function. So it can depend on, so in general, okay, so in general, it can depend on the old coordinate small p and small q, and the new coordinates big Q and big P, and also it might depend on time explicitly. So in general, right? So it can be in this form. Okay. But as you will see, we'll just consider some special case where f does not really depend on all of them. Okay, but we'll see. So this f is what we call the generating function. Okay. So it helps us to generate the transformation as we'll see. Okay. Okay, so now well, I know that this is satisfied, right? So this is my requirement. Okay. So now if I consider the variation of this thing, right? So I can do it term by term, right? So I can do the variation for this first whole thing, and then plus the variation of this second new term here, right? So then the variation of this term, okay, so which is equals to the variation of this f evaluated at the tf minus the f evaluated at the ti. Okay. So it doesn't matter what capital F we have, right? Because this is really is df dt, right? So and then we integrate the df dt. So we basically, right? So taking the anti-derivatives. So now, if we consider this the delta of this, okay, so we'll realize that it will be 0 anyway, regardless of what form of f we pick. Okay. So because the variation at the endpoints, okay, so it's required to vanish. Right. So right at the beginning, when we learn about the calculus of variation, right? So at the starting point, at the end point, you are free to pick any path, right? So, but then you can see that when you vary from this path to this path, right? So these are the variation that we have, right? So, but between these two paths, right? So this point is still the same, right? So this point is still the same. At the two endpoints, right? So no variation. So therefore, this term will be 0 anyway. Okay. So that is to say, right? So if we know that this is satisfied, then adding another term here, this df dt, won't change your conclusion. Okay, so now this is the trick. Okay. Okay, so now we have in the old coordinates, right? So this is what we have, and then in the new coordinates, this is what we have. Okay. So what is our goal? Okay, so remember, our goal, well, ultimately is to find a relation between the old coordinate and the new coordinate. Right? So then we are trying to compare these two integrands here. Okay. So this is true, we know, right? So if this integrand is the same as this integrand, then we know that this is also true. Right? So therefore, we compare the integrand. Right? So the integrand on the left-hand side, go here. The integrand on the right-hand side, go here. Okay. So then these equations will ultimately give us the relation between the old and new coordinates. So first, just look at this generating function f. Okay. So as I said, the f can depend on the old PQ and the new PQ and also T. But here you can see that I'm considering a special type of a special function which only contains small q and capital Q. Okay, so this is a special type. Okay. Only small q and capital Q. So it does not depend on small p and capital P. So looking at this, and by the definition of total derivatives, okay, by the definition of total derivatives, this is what I write down. Okay, no physics here, just a definition of total derivative. Okay. So now I'm going to put this whole thing, okay, so back to the right-hand side here. Okay. So then I have this comparison. And then what I'm going to do is to move all the terms to the left-hand side. Okay, so that the right-hand side only has this 0. Okay. So now on the left-hand side, I'm going to group terms. Okay. So there are 3 kinds of terms. So the first kind will always comes with this qi dot. Okay. So the second kind comes with this capital QI dot. And then the the third kind, okay, so do not come with either of these two. Okay, so right, so for example, right, so these terms they all comes with this qi dot. Okay. So this term always come with this capital Qi dot. Okay. So and grouping terms, right, so you can see that the first group, right, so the Qi dot term, right, so with this coefficient, right, so the capital Qi dot term come with these coefficients, and finally other terms. So now this equation holds if all the coefficients of this Qi dot term, the small Qi dot term and the big Qi dot term and the other terms all vanish. Okay. So that means this is 0. If this is 0, this is 0, and this is 0, then we are done. Right. So that is, these are the requirements here. So these, you can see that they give you relations between the old and the new coordinates. Okay. So because, right, so you can see that this f depends on this small q and this capital Q, right? So then this partial f partial capital Q will be some terms that depends on small q and capital Q, and then I have this capital P here. Okay. So similarly, right? So here, right hand side here, I will have some terms that depends on small q and capital Q, and then on the left hand side, I have this small p. Right. So finally, right, so this new Hamiltonian K is equals to this old Hamiltonian H plus this. Okay. But as you see in our example, okay, so I'm not going to consider the case where the generating function contains t explicitly. Okay, so therefore you can just forget about this for now. Okay. So that is the old Hamiltonian is just the new Hamiltonian. But remember, I'm not talking about the form of the old Hamiltonian being equal to the new Hamiltonian. Okay, so as you see, okay, you see that. Okay. The form will be different. Okay. Okay, so lots of steps here, but let's do examples, right? So that would be easier to really try to get a feeling of what's going on. Okay. So simple example here. So original coordinate. Okay. So this Q and P. So and then now I give you a generating function. Okay. So this is the F1, right? So it's equals to the small q times capital Q. Okay. So now then what is the relation, right? So between the old coordinate and the new coordinate. So just using the formula, right? So from the previous case, previous page. Okay, so maybe missing a minus sign here. Right. So small p equals partial F1 partial small q. Right. So that is small p equals partial Q times Q, partial Q. Then this is just capital Q. And then this similarly, right? So this capital P is just the small q. So then that is the new q is equals to the old p, right? So and then the new p equals minus of the old q. So what one remark here, right? So first of all, why do we want to make canonical transformation? Okay, so last time I think I mentioned it is that we hope that in some situations where the Hamiltonians, okay, so might look complicated, right? So by doing canonical transformation, we might be able to make the Hamiltonian to become a simpler form, which is easier to solve. Okay, so that's always a goal. So, however, okay, in this case, right? So if I make such a transformation, it's unclear how this make things more simple, right? So, but indeed, okay. So at this point, right? So I'm not yet talking about. I'm not yet showing you an example where the transformations is helping you to simplify the problem. Okay, but I'm just illustrating that how the canonical transformation can be achieved by just taking a generating function. Right? So that is, so whether the transformation is helpful or not is another question which we don't worry about it at the moment. Okay. So and the other remark is that now you can see that the new Q, right? So we always think of this Q as the spatial coordinate, right? And this P as the momentum coordinate. But now you can see that the new Q, which we think means the spatial coordinate, is equals to the old momentum coordinate, right? So and on the other hand, the new momentum coordinates is equals to the minus of the old spatial coordinate. Right? So well, you might find it a bit strange, right? So to do it this way, right? So the new position equals to the old momentum. Right? However, it is indeed totally fine in canonical transformation. Okay, so you will see many situations like this, right? So because as I said, when we think about the Hamiltonian formulation, we think of the space, right? So it doesn't matter whether you're talking about the spatial coordinate or the momentum coordinates. Okay, so both of them are the coordinates of the phase space. Okay, so anyway. Okay, so let's do one more example. Okay, so you can take 1 minute to just try it by yourself. So this time I give you a generating function. Okay, so instead of q times q, now is this minus capital Q divided by small q. So then I want you to find the relation between the O and the new coordinates. So that should be quite straightforward, right? So always using the same two formulas, right? So the small p equals partial f1 partial small q. And the other is that the capital P, okay, just to distinguish this capital P and the small p, I'm just going to add a line at the bottom of the capital P, okay, equals minus partial f1 partial capital Q. So the first one gives you capital Q divided by Q square. And the second one just gives you 1 divided by Q. Right. And that is, right, so the new P is equals to 1 divided by the old Q. And then the new Q is equals to OP times OQ squared. Right, so that's it. again, you can see that how the momentum coordinate and the spatial coordinate are always mixed together. Okay, so next, this time is like an inverse problem here. Is that suppose I told you that I have made a canonical transformation like this, okay, and then I want you to find the corresponding generating function. Okay. So one question here, right? So you might ask, so suppose I give you a transformation, and then how do I test whether it is indeed a canonical transformation or not, right? So I told you that it is, but how do you know that you can trust me? So of course, one way to find out is that, as what we are going to do here, is that if you can find a corresponding generating function, then you know that this is a canonical transformation, right? So that's one way, but there's another way which I'll talk about a bit later. Okay, so is that without explicitly finding out the generating function, we can also test whether this a given transformation is canonical or not. Okay. Okay, but let's do it first. Okay. So we always start with the two equations that we have, right? So we know that the small p has to be equals to partial f partial small q, and then the capital P has to be equal to minus partial f partial capital Q. Right. So from these two relation and also what is being given, we want to find out the form of this capital F, right? So first, from here, from the second equation here, let me write down small p equals to small q times e to the capital Q. Right. And therefore, right, so from the first equation here, I have partial f partial small q equals small p, which is small q times e to the capital Q. Okay. And if you integrate both sides, right? So what you get is that this f is equals to integrating this, right? So with respect to small q, that would be 1/2 small q squared times e to the capital Q. Oh, that's not done yet. Plus some arbitrary function which only depends on capital Q. Okay. Right. If you don't understand why this term is here, right, just take the derivative on both sides, then you get back to this. Okay. So now look at the second equation over here, right? So the capital P is this minus partial f partial q. Okay. And first of all, right, notice that this. Okay, so let me write first. So minus partial f partial capital Q. Right, just take this. Right, so that would be minus 1/2 small q squared e to the capital Q, right? So minus dg d capital Q, right? And on the other hand, we know that this capital Q is given here. Right, so this, what is this? So this is minus 1 plus Q squared divided by 2 times small p divided by small q. Right? But we know that this small p divided by small q is just e to the capital Q. Then by comparing this, right, so you can conclude that this dg d capital Q is given by e to the capital Q. And that is, right, so small g is just e to the capital Q plus, maybe plus a constant, but that won't be useful anyway. Okay. So therefore, right, so this generating function f given by 1/2 small q squared e to the capital Q plus e to the capital Q. Right, so now with this generating function, you can, well, you can verify that you can indeed obtain this canonical transformation relation. Okay. Okay, so I have been telling you that this generating function just depends on this small q and capital Q, right? So but I also mentioned that it could depend on a small p and capital P. Okay. So indeed, there are several types of generating functions. Okay, so the one that I told you, which only depends on small q and capital Q, is known as the type 1 generating function. So for the type 2 generating function, okay, so it would look something like this, which depends on this small q, okay, capital P, okay, and also with this additional sum here. And then there's a type 3 and type 4. Okay, so I'm not really going to talk about those. I'm just trying to let you know that they exist. Okay, so they exist. So there are different type of generating functions. Okay, that might be useful in different situations. Okay. If you want more details, okay, you can go to this reference book here. Okay. So now the general properties of canonical transformation. Okay. So the identity transformation is canonical, of course, right? So identity transformation, that means that you are doing nothing. Right? And if a transformation is canonical, then its inverse transformation is also canonical. So that also sounds very reasonable, right? So and then two successive canonical transformations. So that is the, or you can say that the product of two canonical transformations, okay, so is also a canonical transformation. So no proofs are given here. Okay, so but I believe that they all sounds reasonable to you. Okay, okay, so now let's just get to an example where we can kind of see that a canonical transformations can help us to somehow simplify a problem. Okay. So, but of course, in this example, okay, so the problem that we have is already something that is well known. Okay, we know how to solve already. But anyway, so let's try to just really try to simplify this Hamiltonian. Okay, so first, okay, so you can again try by yourself, take a couple minutes, is that I give you this generating function, okay, and I want you to do the canonical transformations, and then, well, this time also find the new form of the Hamiltonian, and then use the Hamilton's equation to find this capital Q and capital P. In the previous example, so I only tell you to do the canonical transformation, but I didn't give you any form of Hamiltonian. So this time I have the Hamiltonian for you also, okay, to see how it actually simplifies this Hamiltonian. Right, so you can take a couple minutes to try that. Well, so again, you are just using the same two relations here, right? To start with these two. Okay, so so first of all, let me just call this capital. Let me just call the x as small q. Okay. So I think you should have already gotten the relation between the old coordinate and the new coordinate already, right? So let me just write down the answer here. So for the small p, that is partial f partial small q, easily find that this is m omega small q cotangent capital Q, right? And then this capital P would be so what is the derivative of this cotangent Q? It is the 1 over sine square. So like this. So then that means, right? So from the second equation here, I would have this small q square. Let me use this small q square as the subject. Is equal to 2 divided by m omega capital P times sine square capital Q. Okay. So similarly, let me also write down the small p square, because I need the most p square, right? So for this term here, right? So small p square would be this whole thing square, which is m square omega square q square cotangent square q. Right? And then you'll find that this is just this. So now that I have this small q square and more p square expressed in terms of the capital P and Q, then I'm ready to substitute this into the Hamiltonian. Okay. So once you do that, if you just do it, and then you realize that this sine square capital Q plus cosine square capital Q is just 1, right? So then you see that this Hamiltonian, now I call this K, right, which is a function of capital Q and capital P, would be just omega times capital P. So then you can see that after transformation, the Hamiltonian is much simplified. Just a linear function in capital P. Right. So and then again, the nice thing is that the same form of the Hamilton's equations will still work. Right. So that is partial capital K partial capital P is capital Q dot. And what is partial K partial capital P? Which is just omega, right? A constant omega. So then you can see that, right? So the equations of motions in the transformed coordinates is very, very easy to solve, right? So Q dot equals omega. So that means that Q equals omega t, right? So plus some constant, right? The constant, let me just call this beta, like this. Right. So on the other hand, right? So the other Hamilton's equations would tell you that, right? So the capital P dot given by partial K partial Q minus partial K partial Q. Right. So the other Hamilton's equation tell you this. Right. And what does that mean? And that means that this partial K partial capital Q is just 0. Right. So that is the capital P dot is just 0. Right. So that is the capital P is just a constant. Okay. Okay, but let's try to finish the problem. Right. So we are not done yet, because now I have the capital Q as a function of time, but ultimately I want to express the final answer in the original coordinate system. Right. So I want ultimately I want a small small q. Okay. So then I use this relation. Right. So now I know that this q is just this one. Right. So I just substitute it back here. So from here, right, so from here, small q is the square root of 2 capital P divided by m omega sine omega t plus beta. Okay, but what is capital P? So as I said, capital P is just a constant. Okay. And you may also wonder then what is that constant? Okay, so in fact, if you look at the Hamiltonian here, okay, so this, even after the canonical transformation, in this case, the Hamiltonian still has the physical meaning of total energy. So originally, right, so this Hamiltonian has the physical meaning of total energy. Okay. Even after the canonical transformation, it's still the same value, right? So because as I show you already, right, so the here, right, so K is equal to H. Okay, so for canonical transformation. But I'm talking about the value being equals. Okay, so but not the form. So you can clearly see that the form of K, of course, is not the same form as H. Okay. But both of them are E, which is the total energy. So therefore, right, so this Q, well, so this capital P, let me just write it as E, right? Okay, so then this is an example on how the canonical transformation may be used to simplify the problem. Okay, so then finally, just to address what I said earlier, is that how do I test whether a transformation is canonical? Okay, so without actually figuring out the generating function. So there's a theorem says that, but I'm not going to do the formal proof, but I'm going to give you some idea. Is that so? If I suppose I do a canonical transformation from this, well, that can be so small p and small q, right? So and then there might be a set of p and a set of q, right? So not necessarily a one-dimensional system, but anyway, from small p to small q, right? So and then get to this capital P and capital Q. So if this is a canonical transformation, okay, so if and only if the Poisson bracket of the capital Q and P, okay, so it's equals to this delta ij. So what does that mean? So remember, in the last part of this chapter, right? So we know that the Poisson bracket of this small p and small q satisfied. I'm sorry. Small q and small p satisfy this relation, right? So this is something that we learned from the last part of the chapter, right? So then, and I call this the fundamental Poisson bracket. Right? So that is to say, so that means this is given already. Okay, so that is to say, if the transformation preserved this fundamental properties of this Poisson bracket, then well, if and only if, right? So well, if this is preserved, then this is a canonical transformation, right? So on the other hand, if this is a canonical transformation, then this relation is preserved. Okay. So that is to say, right? So if I give you a transformation, then and you want to test whether this is a canonical transformation or not, then you just need to try to do the Poisson bracket of this new pair, capital Q and capital P. Okay, so but just to remind you, so then how do I do the Poisson bracket for this? Okay, so you just, again, the basic definition would be this. I'm sorry, I write a mistake here. So there's a mistake here. So this is J, of course. And this is also J. Okay. So QI, PJ, QI, PJ. Okay. So Poisson bracket of this capital QI with this capital PI is this. So this is the right. So remember that this is the definition. Okay, and we are still taking the derivatives. Okay, with respect to this small p and this small k here. Okay. So let's look at one example. So in the second example we've done, right? So this one. So let's try to verify that this is a canonical transformation. Okay. So what we had previously, right? So this one. So the Poisson bracket this and this partial capital Q, partial small q. What is that? That is 2 times p small p times small q. But this partial capital P, partial small p is just 0. Okay, and then minus partial capital Q, partial small p. That would be just small q square. And then a partial capital P, partial small q, which is minus 1 divided by small q squared. So then that would give you 1. Okay. So that verify that this is true. Okay. So let me try to give you the idea of how to prove this. Okay, in general. Okay. Just consider the simplest case where I have just one dimensional motion for one particle. Okay. So after I finish this, and then I'll just give you a break, and then we will start the next chapter. Okay. Right. So I want to show that this is. So I'm just going to show that if I have a transformation that is canonical, then this Poisson bracket is 1. Okay, so I'm going to show that. So again, let me write one more time. So since I told you that this is a canonical transformation, so that means that I know that there exists a generating function. Okay. So I don't need to know what generating function is. But I know that this is coming from a generating function, right? So that is to say, I know that there exists a generating function. Again, I'm just going to use the type 1. Okay, so just as a special case, and I know that these two relations hold. Okay. So as I said, I don't need the explicit form of this capital F. Okay, so I don't need to know that. Okay. So now I will need to find out these derivatives, find out the relation between these derivatives and what I have over here. Okay. So first of all, want to remind you that because there are really different variables here, I want to remind ourselves that, remember, when we take the partial derivatives here, what is being kept constant, right? So small p is being kept constant here. So small q is being kept constant here, right? So here, right? So small q is kept constant here, and here small p is kept constant here. So that is when I take these derivatives. So I want to treat the capital Q and this capital P, right? So as a function of small p and small q. Okay, so first of all, that's the thing. Okay. So now, if I consider this capital partial capital P partial small p, so just using chain rule, okay, so we know that this is partial capital P partial capital Q, keeping small q the same, times partial capital Q partial small p, like this. Why do I need to use chain rule here? Because you can see from here, I write capital P as minus partial f partial capital Q, and this f is a function of small q and capital Q. So that is from this side, right? So you will see that apparently P is expressed as a function of small q and capital Q. Okay. However, right, so over here, right, so I actually need well, we know that ultimately this capital P is a function of small p and small q. So that is right. So this is actually can be written as capital P small q, and then we know that so the capital Q also has to depend on small p and small q. So like this. Okay. Okay. So this is for this term here, and then next I'm going to consider this term. Okay. So this is partial capital P partial small q, keeping p constant. So by using chain rule, right? So that's it. This is what we are doing, right? So partial q is this, right? So then if I apply chain rule, then what you have is that, well, this capital P will depends on this small q and capital Q, right? So then the first term would be this. And then the second term, like this. So now what I'm going to do next is that I'm going to substitute, right? So this whole thing back to here, and then substitute this to here. So then you can see that I have in a total 3 terms. Okay. You actually substitute this and substitute this back here, and then you can see that the Poisson bracket is just this. Just this. Okay. I have 3 terms, but 2 terms will cancel each other. So only 1 term survive this term. And then now, if you look at this partial capital P, partial small q, and then look over here, then you can see that this one over here can be written as a second order derivative, which is this. And then now, this, assuming that, so this f is a well-behaved function, so then the order of the derivatives can be switched. Like this, right? So then this is just this. And this partial f, partial small q up here is just p. So therefore, okay, it's just a product of these 2 terms. And this one is exactly 1 over this one. And therefore, this is just 1. Okay. So then I hope this at least gives you an idea on how it works. Okay, so although this is not the general proof, okay, so but I think that's sufficient for our knowledge here. Okay, so now let's take a break. Okay, so let's take a 10 minutes break, and then we'll start the next chapter. We'll come back at 12:46. Okay, so over the last chapters, we have been dealing some concepts which are quite abstract, right? So all this Poisson bracket and this canonical transformation thing. So in the coming chapter, this chapter 6, we are going back to deal with something that is more down to the earth. Okay, so we are essentially we go back to think about forces. Okay, so the title of this chapter, right, is about motion in a non-inertial frame. Okay, so first of all, a frame means a reference frame, right? So or most of the time we call that a coordinate system, right? And first of all, non-inertial frame, what it is? Okay, so or I should first say what is an inertial frame. So an inertial frame, that means that your reference frame or your coordinate system is either not moving or moving at a constant velocity. So that's what we mean by inertial frame. So then for non-inertial frame, so that means that our coordinate systems is accelerating. Okay. So that's what it means. So we'll be talking about, in this chapter, we'll be talking about two types of non-inertial frames. So the first type that we'll talk about, so which will be the main theme of this part one, is the linearly accelerating frame. So that is, the reference frame is accelerating in a straight line. Okay, so that's linearly accelerating frame. And then the part two, which I think is the difficult part, is that the frame is rotating. Okay. So then let's start with this easier part. Okay. So suppose, right, so I have a particle here. So the particle itself is accelerating, let's say, with an acceleration a. And then this XYZ, this black reference frame is an inertial reference frame. So that is, right, so this is a frame that is at rest. Okay. So then to describe, right, so the motion, right, so of this particle here, right, so by Newton's second law, right, so we have this F equals ma, right, so nothing new here. So now I'm considering the same particle, okay, so doing the same thing, but now I'm using another reference frame, this red one. So this red reference frame is accelerating also to the right, right? So indicated by this green arrow here. So the acceleration of this frame is given by a naught. Okay. So just for illustration purpose, so you can see that I am setting this a naught to be smaller than the acceleration of the particle itself. It does not have to be, right? So, and also in general, we can consider the case where the a naught and this a to be at different direction. Okay, so but at least for the first case, okay, so for easier to understand, just let's say they are in the same direction. So in this frame, so that means that you are an observer that is accelerating together with this red frame. Then what you see would be still a particle that is accelerating, but at a smaller rate. Right. So because this is accelerating, but you are also accelerating, so you're kind of tracing the particle. Then you see that this particle, okay, so it's not accelerating at a. Instead, you see that the acceleration of the particle is given by a prime, which is given by a minus a naught. So remember, we are always doing this vector sum or vector subtraction. But of course, since we are talking about the same direction, then you can in this case you can think about this the scalar subtraction. So therefore, you can see that I am using a smaller arrow to indicate the acceleration in this frame. Okay. So now, if you want to set up the equation of motion, right? So in this red frame, okay. So what would you do? So if you are in this frame, and now you cannot simply just say that F equals m a prime, right? You cannot do that. Right, so this one is correct, F equals ma, but this is not. F is not equals to m a prime, right? So because you know that from here, f is actually equals to m, a can be written as a prime plus a naught, right? So that is right. So f is equals to m a prime plus m a naught. F is not equal to m a prime. So, however, suppose if you still want to express, okay, so the equations of motion in a way that looks the same as f equals ma, then what you can do is the following. Okay. So here I am going to define, okay, an effective force, okay, F EFF, okay, so which will be equals to MA prime. So then what it means is that, right, so this F effective equals to MA prime, and that has to be equals to M times A minus A naught. And this MA, the first time you know that this is the original F, right? And the second term, right? So minus MA naught. So then from here, right? So you see that this F effective will be equals to the real force minus the term. Okay. Then if you do that, you can use the form F equals MA, right? So in this accelerating frame, right? So that is, right? So F effective is not just the real force, but with an additional term. And I'll call this additional term minus MA naught to be the so-called the fictitious force or the pseudo force. So this pseudo force or fictitious force has nothing to do with the interactions between different objects. Okay. So it's not because something is pushing or pulling this thing, right? So it just really is a mathematical terms. Okay, so that you can still use the form F equals MA in this non-inertial frame. So can we feel this fictitious force? But this is not real, right? So just think of the following. Okay. So you might have the experience that no one is pushing or pulling you, but you had the tendency to fall. Okay, so when did you experience that? Just think of taking MTR, right? So when you take MTR, right, so you are just in the train, right? So standing, let's say, right? So if everything is normal, right? So then suppose that this is moving at a constant velocity v. So now suddenly, if something happened, okay, so such that this train has to decelerate suddenly, right? So then what happened is that you might have that experience, right? So when it decelerates suddenly, right? So then you have the tendency to fall to one side. So nothing is pushing or pulling you, right? So but you have the tendency to fall. Okay. And you understand that this is really because of your inertia, right? So then I think you might have so deceleration, sudden deceleration, I think is something that we have experienced more often than sudden acceleration, right? So I guess when you take the a car or MTR, usually it doesn't accelerate suddenly, right? But sometimes it will decelerate suddenly. But anyway, so this is our experience. Okay, so about the fictitious force, right? So what happened in this case, right? So in this case, right? So the car, the train, decelerate suddenly. So that means decelerate. That means that it has the acceleration to this side, right? So when you have the acceleration to this side, then the fictitious force, the pseudo force, right? So will be to this side, right? So minus ma, or let's call it a naught, right? So that's the fictitious force. And your tendency to fall is along the direction of the fictitious force. So let's work on some example. Okay. Right. So suppose I have this car, and then inside the car, I set up this pendulum here. Okay. So originally the pendulum is just hanging vertically, without any motion. Everything is at rest. So now the car starts to accelerate at this rate, capital A. Okay, so to the right. Then what happened is that this mass, this pendulum, okay, so will be at an angle with the vertical line. And I want to find out what is this angle, and also what is the strength in the what is the tension in the string. So I'm going to do this problem with two different methods. Okay, so the first one is just with what we have learned before, so without any fictitious force. And then the second, we'll use the concept of this fictitious force, and then show you that you can arrive at the same answer. Okay. So method one. So I'm just using an inertial frame. What I mean is that you just imagine that you are a person just standing on the ground. You are watching the whole car is accelerating. Okay. So now, if you just draw the force diagram, so it looks something like this, right? So the mass has its own weight W, right? So and then this string is making this angle here theta. So that's why the tension is to this side. Okay. So now if you go to just resolve the components, right? So in the horizontal and the vertical direction, that's what you get. So first of all, in the vertical direction, right? So T cosine theta has to balance the weight W. So that how I get the first equation here. And then the horizontal component of the tension has to give the force to make this mass, to make this ball accelerate. So right, so then the T sine theta has to be equals to ma. Right. So then just solving these two equations with two unknowns, then I got the theta and also the tension. Right. So in this method, so nothing is new. Right. So I believe that you might have seen this. Okay. Okay. So now let's consider the non-inertial frame. So that is to say, now you are sitting in the car, right? So accelerating together with the pendulum. Then this time, you see that nothing is moving. So that now you see that the mass is not moving with respect to you, right? So because you are also in the car, so you are accelerating with the pendulum together. And then now, here you will have an additional force here, which is the fictitious force, right? Because the acceleration of the car is to the right, right? So the fictitious force is minus ma. So that is the fictitious force is to the left. Okay. And this fictitious force, the magnitude is ma. Okay. So now I look at this picture. This is my force diagram. And then I again resolve the force component in the vertical and the horizontal direction. Right. So the vertical equation is just the same one. Okay. So now the horizontal equation, right? So instead of this t sine theta equals to m times the acceleration. So now I have this t sine theta equals to the fictitious force. And in fact, right, so that fictitious force is just the magnitude is just ma. Okay. So then you can see that in this set of equations, I obtain the same result, right? So then, of course, you might ask, okay, I can do it in both ways. How is this more convenient than this? How does it really help us? Okay, so then let's look at the next example. Let's look at this example. Then it might be more clear how using the concept of fictitious force might give us convenience in some problem. Okay. So this example use the same setup as the last example. So now the whole thing is also already accelerating. But this time, I allow, right? So I make this mass to perform a small oscillation like this. Okay. So in the previous example, right? So the angle between the string and the vertical line does not change with time. So now I give some small kick to this mass so that it perform a motion like this. Okay. And what I want to study is the oscillation frequency of this motion. So if the whole car is at rest, right? So you know that the oscillation frequency omega is just given by square root g divided by h, right? So h is the length of this string. So now I want to show that with this accelerating car, okay, so the oscillation frequency is actually given by this instead of this. Okay. Right. So to do that, so I need to set up, right? So study the equation of motion of this mass. Okay. So again, I'm going to start with the method with using the inertia frame. So no fictitious force, no concept of fictitious force yet. Right. So again, so that means again you are standing on the ground, and then so this is the coordinates that I'm going to use. Okay. So you can see that I have this xy coordinates. So this xy coordinates would be the coordinate system that is moving with this box. This is the car, okay, and this is the origin of that coordinate. And also, I have this capital X here. So what it is? So this vertical line is just a fixed reference line, and then this X measure, let's say, measure the distance between this fixed reference line and the midpoint of the car. Okay, like this capital X. And you understand that the X capital X double dot is just given by this constant capital A. Okay. right? So then the position of this mass here would be given by capital X minus small x. Small x is the x position of this ball, so in this coordinate system. Right, so now let's try the two directions, right? So the forces and the equation of motion. So for the vertical direction, so nothing. What I have is again these two forces, right? So the weight and the vertical component of the tension, and that has to be equals to m times the vertical acceleration of this mass, which I call the my double dot. Okay. And then along the horizontal direction, right? So the only horizontal force again is the t sine theta, and that has to be equals to the acceleration of this ball, right? So with respect to the ground observer. So that would be the second order derivative of this capital X minus small x. And that would just be equals to m times capital A minus x double dot. Okay. So at the end, right, so you understand that using x and y won't be the convenient choice to describe the motion of this pendulum, right? So I ultimately I want theta. So then let me write down the relation between. Okay, so this is just okay. So first of all, I'm just going to, from these two equations, I'm going to eliminate t, the tension t. Okay, so then I got this one. So then the position of mass, right? So in terms of theta, it's just given here. Right, so x is just h sine theta, y is just h cosine theta. So one thing to take note is that I'm considering, in this case, I'm considering going down as the positive y. Okay, so that's why I don't have minus sign here, just for convenience. Okay, so here you can see that I already have an equation of motion, but I still have this x and y here. At the end, I want to have this equation of motion to be expressed in terms of theta only. Okay, so that's why here you can see that I start from this relation, and then I'm able to just take the derivative, get the relations between x double dot and y double dot with theta. Okay, from this step to this step to this step, it's just taking derivative 2 times. Okay. Okay, so then now I'm going to substitute these equation 2 and 3 back into 1. Okay, so this long one, but luckily you can see that some terms will get cancelled. Then at the end, this theta double dot is given by this. Okay. So if you don't have the last term, you realize that this is just the simple pendulum that you are familiar with, right? So with a fixed period, right? So now I have this, in this equation, I have this additional term here, right? So, and if I want to study the oscillation frequency, if I want to get the oscillation frequency, so at the end of the day, what you expect is that you get the second order derivative of the angle equals some coefficient times the angle itself. Okay, so for now here I have this additional term here. So one thing to notice is that if you have a fixed car, right, so not being accelerating, right, so then you understand that the equilibrium position of this pendulum is the vertical line, right? So however, now if I'm going to actually, let me let me draw it to the other side. Now, if I'm having this accelerating car, right? So from the previous example, you already understand that the equilibrium position won't be a vertical line, but instead a line like this, right? So, and then your oscillation is something like this, right? So therefore, we will not use this data. Okay. So because data, what is data? Data would be the angle between the vertical line and the position of your string. Right, so that's not a convenient choice actually. So instead, what I'm going to do is that I'm going to use this angle to be our variable. You can see that this angle is the angle between my string position and this equilibrium position dash line. So I'm going to call this alpha. And also, I'll say that this blue dash line, the angle between this blue dash line and the vertical line, this I will call this theta naught. Okay. So that is, I'm going to let this theta to be equals to theta naught plus alpha. Okay, look at this diagram. Okay, might be a bit small. Okay. So, and I assume that alpha is much smaller than 1. Right. Small oscillation. Right. So here, so in the original case where we don't have any acceleration, right? So we always, so this is the data, and we always just say that data is much more than 1. But here, data itself is not necessarily much more than 1, but the alpha will be much more than 1, right? So because the data itself no longer tell you the angular amplitude of the oscillation. Instead, alpha would be the parameter that tells us the angular amplitude of the oscillation. Okay, so then theta equals theta naught plus alpha. And now theta naught is a constant. Remember what theta naught is. Theta naught is actually what we get in this problem. Okay, so theta naught is actually arctangent of A divided by G. Okay, so just to remind you over here, tangent theta naught is just A divided by G. So that is a constant anyway. Okay, so now theta equals theta naught plus alpha. So that means theta double dot is equals to alpha double dot. Right, so because the theta naught is just double dot is 0. So therefore, the left-hand side of the equation becomes alpha double dot instead of theta double dot. And then for the right-hand side, this theta is written as theta naught plus alpha. Right, so this one also. Okay. And then by Taylor series. Okay, so by Taylor series, right? So this sine theta naught plus alpha written like this. This cosine theta naught plus alpha written like this. Drop the terms of alpha square and any higher order term. Okay. So then with grouping terms, I'm going to group the terms with alpha together and then plus other constant terms. So then now I want to express this cosine theta naught in terms of G and A. Right. So because tangent theta naught is A divided by G, right? So like this, let me draw a triangle. So this theta naught, the tangent theta naught is A divided by G. So that means I'm going to draw a triangle like this, right? So then this is the longest side is the square root of A squared plus G squared, right? So that's why cosine theta naught would be G divided by this square root, right? So this sine theta naught would be A divided by this square root. So like this. And then finally, I have this alpha double dot equals this coefficient times alpha plus a constant term, right? So you know that the constant term does not affect the oscillation frequency, right? So all it matters is the coefficient in front of the alpha. So then you can see that, right? So this thing here is the omega squared. So therefore, right? So omega is just the square root of this. So it took us quite some effort, okay, so to get to here, but we did it. Okay, so last time, okay, so I'm going to solve the same problem, okay, but using the accelerating frame. Okay, so then and show you how it will become a more convenient problem to solve. Okay, so I'm going to stop here.